So till now, we have discussed about the interaction of atoms with background quantum fields, and we have seen that as a result, the atom makes transitions across its excited and ground states with certain probabilities, and we can define a transition rate for this procedure to happen. And we obtain the expressions like this, where the mod square of the transition element, the monopole coupling term m, gets squeezed between excited and the ground state of the atom, mod square, and times these sign functions at the argument delta E upon h bar plus omega k naught and delta E upon h bar minus omega k naught is the transition probability if the background field is present with a particle in it having a momenta k naught. So this omega k naught, which we are seeing over here, is the frequency of the photon available in the field. Now, in infinite time limit, by that we mean the time scale larger than the internal time scales but smaller than the second order corrections to kick in. These expression sign functions approach the delta function's behavior such that the only second delta function which will come from this sign function will survive. Otherwise, it would become 0. So if the frequency of the photon matches with the frequency gap of the atom, then only a transition is possible. Otherwise, the atoms will not get excited. So probability of ground to excited transition or a rate of ground to excited transition would be 0 if in infinite time limit, if omega k naught is not commensurate with delta E upon h bar. That we have seen in the previous discussion sessions as well. So this is the expression we obtained for large time limit. By infinite time, I again repeat that we mean really large time scale, larger than the internal time scales, but smaller than the time scale where perturbation theory breaks off. Now, there is another interesting set of events which happens if there is additional set of states at the excited level. Let us say the degenerate states. Suppose there is a one ground state, but excited states are multifold. They all come up with the same energy, and they have degenerate structure. So then we need to ask the question of transition probability across each of them. Suppose I want to ask what is the transition probability across ground state to excited state number 1. Then the similar kind of expression like this will come about, where the transition element, the matrix element of M, squeezed between the ground and the excited state of our choice, E1, let us say. That mod square will decide the rate of transition. Similarly, for second excited state in the sense of same energy, but out of the many excited states, the second one, the transition rate will be determined by the M squeezed between E2 and the G mod square, and so on. For a case in point, we can think of a hydrogen atom, where if we are thinking about an unperturbed hydrogen atom, then 2px, 2py, 2pz of hydrogen atom, all of them come with the same energy eigenvalue. However, depending upon what kind of operator we are putting in, some operators can survive between the ground state and 2px or ground state and 2pz, but may not survive between ground state and 2py. So in principle, these kind of things has to be computed for all the excited states, and then when I sum over all the possible excited states, what do I get as an expression would be the total probability of migrating to any of the excited states. And therefore, this rate which we have written over here is telling us about as the rate of possible transition across any of the excited state from the ground state. Again, the matrix element here would control the transition probability, but a meaningful or a necessary condition would be forced by the delta functions in large time limit. The photon frequency should match. The photon means the particle present in the background field. Its frequency should match the energy gap, otherwise no transition will take place. Okay. Now, this is for the case where the photon in the field has one definite frequency. That means the state I am talking about of the background field is 1k naught. Now, suppose the case where I do not know the state in the field with surety. That means when I am writing this 1k naught, I definitely know that there is only one particle, and that one particle is necessarily present with the frequency k naught. No other frequency is allowed. However, that is not the case physically we expect. Always we will have some spread of probability of having this frequency or that frequency. So in principle, I would only know that the photon or the field has a particle whose frequency is most likely to be k naught, but it could have some spread about k naught. That typically is captured by a spreading function f of k. So I write a well-defined state as psi, which will have an integration d3k, your uncertainty of knowing which frequency it definitely has. So f of k will tell you the spread of frequency and then what are the possible kets associated with that. So this is a superposition over all single particle excitation with different frequency. One of the frequency might be tightly supported, most of the frequency will not be so strongly supported, but this is a well-defined meaningful state. We have seen through previous examples and assignments that this state 1k naught is not a normalizable state. Its normalization is a delta 0. That means it's a non-normalizable state. However, this kind of a state, as you might have worked out in the assignment, you know that the normalization of this state is controlled by the integral property of fk mod square. So d3k fk mod square has to be smaller than infinity for normalizability. So this is a physically meaningful state, and in this, if I want to compute what is the state, what is the probability of transition and what is the rate of transition, I need to compute the 2-point function of the field. Remember, when we were doing this transition probability business, what we realized that some kind of Fourier-like looking integral transforms of the 2-point functions comes about. In 1k naught, when I had put in, this is how the delta functions of these two kinds or the sine functions came about. Now that we have replaced the in state or the initial state of the field with this expression over here, we should recompute what is the 2-point function of the field in this new state. This is a simple, easy exercise for you. So I'm just writing it out. You should be able to prove it that the 2-point function of this state is, there is a one piece which is exactly like the vacuum 2-point function times the normalization of the state. This is the state whose normalization is controlled by the mod square integral of this fk. So this normalization comes here. If the state is fully normalized, that means this integration fk mod square is 1. The integral piece attaching here will become 1. Then it becomes just the 2-point function of the vacuum for a stationary particle. Remember, there was a ik dot x minus x prime thing which I had put to 0 because I was looking for an atom at rest whose x and x prime at different times will be the same. In addition to this vacuum piece, now you will have two more pieces which are of the complex conjugate in nature. First one will be the fk modulated with the mode function e to the power minus ik dot x divided by root 2 omega k. That, and similar thing for fk star, fk primed star in e to the power minus iota k primed x. You can see these two are almost complex conjugate of each other, this and that. However, one thing is computed with x primed at location x primed and one thing is computed at location x. So they are not exactly complex conjugate of each other, but they are complex conjugate and time apart or position apart. So one piece is this and another piece, the complex conjugate of that will come about. That will totally determine what is the 2-point function of the field in this state. This is a homework exercise for you, which will be a part of assignment as well, that you should be able to work out. Okay. So now in this state, we compute the probability as before. You have to do this integral transform for the 2-point function. We have rewritten the 2-point function for this state like the vacuum piece, assuming the state is fully normalized. That means the integral which we were talking about, this d3k fk mod square integral is 1. So under that assumption, first piece becomes just a vacuum piece, vacuum 2-point functions plus state dependent corrections. These two terms are complex conjugate of each other, out of which the product is almost complex conjugate as we discussed, only for the fact that they are at two different times. Otherwise, they are exactly complex conjugates of each other. But the extra term which is obtained is exactly the complex conjugate of the whole thing. All right. So this is the vacuum piece. All the information that it is not the vacuum state but some excited state with a superposition of frequency comes through these correction terms with fk dependencies. Recall the fk tells you how much spread in the frequency of the excited photon is. If there is no photon, fk is 0, let us say. In that case, here only the vacuum piece will survive. The state will be in vacuum state. Okay. So far so good. Let us do the computation once more for this normalized state. Again, the first term, as we have discussed so many times by now, will give me a square of the delta function with positive argument. That is how in vacuum there was no probability of going to excited state. So the term over here, after this integral transforms, that we have done so many times by now, so that you should know how it becomes. Actually, it should become twice of pi square times, actually not twice, 4 times pi square, which I have written. So let me erase it out. So there is a 4 times pi square, which I have written but could not see. So this is the correct expression. So the first term comes from the integration of the vacuum piece with the time integrals over here. You will get that term, and this identically vanishes because the argument of a delta function is a positive quantity. So it will not survive, giving you zero transition probability for vacuum piece. However, now there are two more terms, complex conjugates of each other, which will give me two kind of integrals which are over here. The operative piece, if you look for atom at rest, here only e to the power minus I omega t comes about. Here e to the power plus iota omega k prime t prime appears, and the complex conjugate of these quantities appear over here. So when I go to do this time integral, again like before, you can see you can club out all the exponentials of time at one place. This integral over here gives you this delta function, positive argument again, and the integral over here with t prime combines with the integral over here in t prime, again gives you a delta function with yet again a positive quantity in argument. So again, the first term, the first correction term of the non-vacuumness, the excited state information, comes in two pieces, as we have seen. The first piece also gives you terms which are proportional to delta function with positive arguments. That means they are also going to go out, they are not going to contribute anything. However, the last correction term, which is complex conjugate of this term over here, that survives. You can see that if I look at the t integral has e to the power minus iota delta e upon h bar times t over here, and e to the power I omega kt. So there are sign difference between that. That's why when I do the long time integration, I will get a delta function with potentially vanishing argument, delta e upon h bar minus omega k. Remember, what was omega k? Omega k was a running frequency. We had said that I do not know what is the state. It could have any frequency with some distribution f of k. So therefore, omega k becomes frequency of a photon. All the photons of different frequency are present, determined by their strength from the function's value at that frequency, f of k. So omega k is a running frequency. As the k changes, omega k changes. So there is a possibility that one of the photons would have the same energy as delta E upon h bar. And that photon's contribution Fk decides how much would be the transition probability. So you see the third term over here has exponential with proper signs, so that the integrations over time gives you a delta function which can survive this time. It will survive only if there is a non-zero value of the function f at the frequency of resonance. So you do this integral again like before. This is a simple enough integral we have seen so many times. You will be able to show. This time I am going to get an answer. Again, the mod square quantity of the monopole operator squeezed between excited and the ground states. Everything like before. Make use of the two delta functions in computing the d3k integrals. Okay, and from there we would be able to show that you'll be able to show from here that this delta function takes care of the first d3k integral, and this delta function takes care of the second d3k integral. So here there is a 2 pi from here, there is another 2 pi which is coming from here, which will go and fight with the 2 pi over here. The d3k integral is also 4 pi k square dk, if you recall. So there will be another 4 pi square from these two integrals. One integral will give me 4 pi k square dk, and this integral will also give me 4 pi k square dk. So there will be 4 pi square from here, and there will be 4 pi square from here as well, because the d3k integral. And then I have a k square dk integrals. If you pay close attention to that, I have a k square dk, and this delta function therefore will give me delta E upon h bar square factor extra from the result which I had written, and divided by the twice omega k naught, which is the correct quantity. So there is an extra piece of delta E upon h bar whole square which will come from writing this d3k integral, which is 4 pi k square dk, and then there is a dk integral is same as the d omega k integral, and therefore the result what I have written should be corrected for another delta E upon h bar whole square term. So now you see the correct answer is of transition for this time is determined by all the transition matrix M's squeezing value, but crucial quantity is this f omega k naught mod square. So it asks the state of your choice. This is the state of your choice. It asks the state of your choice what is the value of fk at the transition frequency gap, f of omega k naught. F of omega k naught being the same as delta E upon h bar. So it asks what is the value of the function, its mod square comes about, and that determines what is the transition probability. So again, let me write down in this color, there is a, let us call it omega naught square term as well, omega k naught square term as well. As we discussed, that is coming from 4 pi k square dk integral. There was a 4 pi square quantity here as well. Okay, so actually it would be 4 pi omega not 4, because this will give me k naught square and this will also give me k naught square. So forget about this extra frequency factor. That is not the crucial quantity we want to discuss over here. The crucial quantity is the information of the states, contribution at the resonance frequency. If f of k has a value 0, that means there is no photon which is excited with this much of frequency gap, then the transition probability becomes 0. So it necessarily asks for the probability of finding a photon at an appropriate frequency. Remember, if you compute the probability of finding a photon at different frequency, fk mod square tells me that. So ultimately the transition gap, the transition probability looks for a presence of photon of appropriate frequency, and mod square of that means the probability of that photon's occurrence, determines me the probability of transition as well. So that is natural to expect, and that's why the computations also suggested. All right. And as we discussed, if there are more than one such excited state, we should sum over all such possible excited state as well. So again, here also there is a 4 pi omega naught square whole square kind of correction term should be there. But anyway, do not worry about this factor too much. We can absorb that 4 pi omega naught square in the redefinition of function f as well. But the crucial point is this: everything now depends on the transition gap. Transition gap frequencies photon. If the photon with the right frequency is present, the probability of transition will happen. And if there are more than one excited states present, the transition probability we are computing for all of them. So E1, E2, E3, and for all of them we should be able to compute the quantity which is over here upstairs, and that should give me the probability of transition. Now suppose we are asking for not only degenerate excited state but also excited state with slightly different frequency. Suppose there is some set of a degenerate excited states E, 3 of them let us say, which have all the same energy, and there is another set of excited state E primed which are slightly different in energy compared to E, but they are also degenerate, 3 of them of that kind as well. Then if I ask for the probability of transition from ground state to any of the excited states, then the same computation would be carried out for all these excited states. Only thing that I will separate out the summation into 2 sets of excited state. Excited state with the energy E1, let us say omega k naught, energy gap is omega k naught. Again, remember everything has to be corrected with 4 pi omega k naught squared whole square. Okay, and similarly here as well, omega k naught primed square whole square. So the first set of terms talks about excited state with energy gap omega k naught, and the mod square of finding a photon of that probability counts, while the second summation counts over the probability of finding a photon with the energy gap corresponding to this transition omega k naught primed. So together all across different excited state. If the photon of any of these frequencies are present, one of the transitions will take place. And in case there are many such excited states, suppose there is another set of excited state, 4 of them, E double primed and so on, then the same computation will be done for that, and summation over E double prime will also come out. So ultimately, if all the transition elements, let us say this is same for all E1, E2, E3, or E1 primed, E2 primed, E3 primed, if that is same across all excited states, then what will only happen that this probability will become the same for all the same level energy eigen states. So it would just count how many number of degeneracies are there at level E, at level E primed, and so on. And that is how we write the total transition probability would be summation over all the excited states times their degeneracies. So this expression, again with a correction factor of 4 pi omega k naught I, this time I'm writing, because I is the summation index for the excited state as well. So all this for all different types of excited state, the degeneracy of that kind, that excited state kind, comes into the game, and this is the transition probability across one of such excited states. And this is how the summation over degeneracy times all the possible excited states gives me the total probability of transitions across any of the excited state. Okay, so this is as straightforward as we can see, and that is how we can get the probability as well as the rate of transitions as well. Okay, right. If we carry on the game for the continuous case in the same fashion, then the summation over here over the discrete set of excited states converts itself into integration, and NE over here, which was counting the degeneracy at each discrete excited state, becomes the degeneracy density function G of E, and then the usual integrals up to a 4 pi omega k square whole square multiplication. Okay, so this is how the continuum case is also dealt with. If I have a set of a continuously distributed excited state like this, and I have a ground state, the probability of transition across any of these from the ground state will be computed like this. One crucial assumption is that for each excited state with energy E, the matrix elements of transition is the same. That's why the G of E function has been multiplied. If different excited states, meaning at energy E, let us say there are more than one excited states, and then there is a degeneracy like that. Then across all of the excited states, the transition matrix element is the same. Then only this number multiplication or degeneracy multiplication works out. Okay. Now, just for notational convenience, I am going to call the ground state of the atom as 0A. 0A is the ground state of the atom, and excited state is E, such that I don't have to write delta E all the time. I will just write E. E means energy gap between the ground and excited state. I am redefining the base value as the ground state value of the atom, ground state energy value of the atom. This is just a notational convenience. Now, all this 4 pi omega k square whole square thing was coming from the d3k integral, which I had not completely written correctly, which was coming from this d3k, 4 pi k square from this and 4 pi k square from this. So if I go one step back, that means I do not do this d3k integral and look for only finite time integral. These three terms which were surviving here, this was giving me a delta function. This was giving another set of delta function with positive argument. Only the third term was giving me the proper delta function with non-positive argument. These things for finite time integration convert themselves into sign integrations that we have seen in the previous class, that you know by now as well. These integrals are just the sign functions. So let us focus on the last term only for this two terms for this time. The first two terms anyway in large time limit, they become suppressed functions of a positive delta argument. So therefore, I am not going to pay much attention to them even for finite time, despite they might have non-zero value. But that would be subdominant corresponding to the last term. So let us first focus on the last term for finite time duration, and let us see what is the structure we get to see as a development. So in the finite time integral, the last term will convert itself into sine integral, the sine mod square integral, and I will have a sine delta E upon h bar minus omega k. Only thing is delta E is being written as E this time because of my redefinition of energy. So otherwise I will have this integral as coming from the last term of the transition probability. Again, to remind you, there are for finite time, the first vacuum term and even the first correction term is also non-zero, but for the time being, I'm just looking at the third term, which is anyway much larger than the two corresponding terms. So if I rewrite this mod square over here, this is the integral whose mod square is being computed. That means integral and its complex conjugate. So let me write down the integral and its complex conjugate. So this is just the rewriting of the same expression. I have just split apart the mod square term. Mod square is z times z star. So I have written the first integral and its complex conjugate integral separately. All right. Again, be careful that there is always a 4 pi omega k square thing which was initially missing. This time they have gone into d3k. So this is not a wrong statement. This was missed only for large time duration when I made use for the delta function. So this expression is fine despite the previous expression missing out on this 4 pi omega k square. All right. If I take this f of k over here, and actually let me make correction over here. Let me write down divided by 4 pi omega k square. So if I take this f of k, then you see the integral over here will just become dk times delta k minus k naught. This omega k square will exactly cancel the 4 pi k square thing coming in the d3k integral, and this 2 omega will exactly cancel the denominator root 2 omega in each of the term. So what will happen if I make f of k, if I choose to be of this kind? Then two things happen. First, my state will become a single frequency state. That means the state which we were discussing initially over here will just become a k naught state up to a multiplication of probably 2 omega k naught or something. But anyway, it would be just a single frequency state. And as a result, the integral which we are looking at the moment over here will just become an integration over k delta of k minus k naught. That means it will convert all the omega k appearing in the expression as omega k naught, and the second integral will convert all the omega k primes appearing in the expression into omega k naught. So ultimately I will convert this integral for a single frequency excitation into this nice expression over here, where all the running integrals d3k and d3k prime have been performed with the use of the delta function, and I have got this expression. This is simple enough expression to deal with. You can just do a variable transformation. I can define the argument of the sign which is appearing over here as beta. So whatever appears as the argument of sign, I'm going to call it as beta. Okay. And then the simple variable transformation game, the dE will be converted into 2h bar times d beta times t. I'm keeping the omega k naught as I'm treating the omega k naught as a constant because this is the single frequency excitation. There is no uncertainty now. So once you do this variable transformation, it is very straightforward to show that the resulting expression is this, where dE has been replaced by 2 beta times this extra 2h upon t factor. The GE becomes some other function of beta. I'm just writing the mod square term as E, but ultimately E is a function of a beta as well from this expression. And the sine sinc function which was appearing over here becomes sine square beta upon beta square with an extra t square by 4 because there was no t by 2 in the denominator. So when I write in terms of this will become E upon h bar minus omega k naught will just be beta upon t by 2, and whole square of that will throw me t square by 4 factor. So you can see there is a trade-off happening between the t. So there is a t in the denominator here and a t square in the numerator over here, which leaves me a t in the numerator, and there is a h bar in the numerator over here and h bar square in the denominator here, which leaves me with a h bar in the denominator over here. So you can see there is a trade-off, and as a result what I get as probability of transition becomes linear in time. This is one of the observations Fermi had, which leads to something called a Fermi's golden rule, as we will see as we go along, that The probability for this specialized case where I have a single frequency and I have this kind of conditions, then I would get for finite time a linear rise coming into the game. The remaining things are integrals are independent of t. Beta is just a running index. I can compute the beta for the true range of the spread of the eigenstates, or in principle, many of the times it is extended up to infinity, as we will see. But anyway, the crucial factor is this: after the variable transformation, all the t dependency has come out, all the h bar dependency has come out, and therefore I have a rate which is, I have a probability of transition which is linearly proportional to time with some integral value which will give me some number, but at the end of the day, linear rise in time, and therefore the rate will be just derivative of this or division by t, which both of the thing are same. Spontaneous rate or average rate is the same thing. This becomes this nice expression, the integral of d beta degeneracy functions version in beta parameter, and this transition element one has to write in terms of beta as well, and sine square beta upon beta square. So this integral one has to perform, otherwise this whole thing 1 upon 2 pi q upon 4 h bar times this integral is the rate of transition for finite time coming from the third term. Remember, there was a vacuum term and the first correction term as well, which I am treating as a subdominant. You can verify for yourself, those are not highly contributing things. So dominant rate of transition is this. Okay, so now let us go ahead and compute this quantity as accurately as we can. That would give me the exact expression for the rate of transition. However, there is a cute trick one can play off, which is from the realization that the degeneracy of states, g of e, the function which is appearing over here, g tilde of beta is just the re-expression of g of e in terms of beta. And this thing which is appearing over here, em0 squeezed between, which is excited and ground state, the ground state of atom. These things are typically very slowly varying functions of E. However, the function which is appearing over here, sine square beta upon beta square, sinc function, that is highly oscillatory function of beta or E. So if I plot these things, the blue one over here is a sinc function, sine square beta upon beta square. That will have a very high maxima at beta is equal to 0. This is value 1. Then it will be quickly dampen out. This you might have seen in diffractions and other things as well. This is highly suppressed function. You do not get to see much of oscillations. This quickly dies down. But both of these, typically, g of e, remember, is 4 pi k square dk in free space and those kind of things, the degeneracy factor. Or in hydrogen atom, it will become not very rapidly rising function. Across very tiny energy gaps or tiny energy settings, it will change marginally. So you can see both E, M, G and G of E, both these quantities do change in energy, but very slowly compared to this sinc function. So what you can see here, when we were doing this integral, initially the integral was over the energy dE. From where to where? This was from, let us say, minus A2 or minus A2 plus B, which is the energy gap of the excited states. So figuratively, let us say this was the ground state, and I was talking about energy, let us say EA up to EB. From here to here, the energy integration was running, not minus A. Let us call it, this integral was running from EA to EB. Correspondingly, the beta integral will run for some finite range as well. So let me draw the EA over here and EB over here. So initially, I wanted to compute the integral between EA to EB, and in this, there were three energy dependent functions. One was G of E, other was this squeezing of the matrix element, and then squeezing of the monopole operator, and then the sinc function. Now, either you can go ahead and do this exact computation by knowing the exact form of G and knowing the exact form of the matrix element and do this integral. Or what can be done just to get a quick ballpark value is to approximate this integral with something. So what I see, the sinc function quickly dies down to nothing. That means most of the integral's contribution is coming from the first peaks region only. In the second peak, there is some contribution, but that is highly small compared to the first peak's contribution. So what I do, I just do not use this integral, but I can use the corrected approximation. I'm going to think that this EMG, this orange kind of thing over here, is almost a constant, and similarly degeneracy of state is also almost a constant, and then I leave the sinc function as it is. Of course, I am doing an error in this. However, most of the error is not coming in this region. Here I am treating it as exact constants here, which is roughly the case. Here on here, they do not change much. Much of change will come from here up to here. If I had computed the integral fully, then the value of g of E, let us say here, and g of energy here will be much different. So my approximation will become bad across large energy separation, but sinc function comes to save me. Wherever the approximation becomes bad, the sinc function has gone down to almost nothing. That means the weightage of the error portions are very small. So I can safely approximate this correct integral with this. They are not very apart. Most of the difference between this exact thing and this approximate thing lies in this regime, where anyway the sinc function will not allow you to get any meaningful number out. So therefore, what I can do, I can take g of E and this matrix element as constants of E and pull out from the integral. So I had the thing which is inside. I'm saying that they are not changing much. So I can define a central value of them. I can take a base central value E star. I can compute G at this value and say that at remaining values of E, running value, it is not much different from G of E star. Similarly, the matrix element I can compute at E star, and I can claim that the matrix element's value for the remaining integral is not much different from the matrix value at E star. So I replace the G and the matrix values with their E star value, where E star is one of the energy eigenstate in the excited set, and saying that remaining things are exactly the same, not exactly, but very much close to being the same value. So therefore I can pull it out from the integration, and then I am left with d beta integral. Anyway, now I can extend this integral from minus infinity to infinity. I'm adding on this tail and that tail, but sinc function is allowing me to only contribute very marginally. So just for getting a order of magnitude answer, I actually wanted to compute this quantity, but after these approximation, the statement is it is not going to be much different from this integral. This is one useful way of computing things, and ultimately you know that the sinc function integral is very trivial. This is a standard sinc square integral, which you can work it out or look it up. It will just give you some 2 pi factor, which will be which will give you some up to 2 pi factor. So you will see that rate of transition in this case is directly proportional to one of the energy excited state value and the degeneracy function over there, and times the matrix element. So the matrix element mod square times the degeneracy factor divided by h bar up to some numerical constants give you the rate of transition. That is Fermi's golden rule. This is very useful in looking at atoms and other things, because you can quickly look at the degeneracy. This is the degeneracy of the field state, how your fields are distributed, how many states are there for the field at energy E star. You can just compute that. You can look from the D3K integral that how many states are there for at E star, and you have to just compute one of the transition matrix element, and then by assuming most of the excited state transition matrix element are the same, you can quickly multiply these two things, divide it by h bar, and then 2 pi q and whatnot, and you will quickly get the rate of transition for those atoms. So this is a very powerful tool in knowing the transition rates for atoms dealing with photons present in the field. This is ballpark, gives you very right value. It is not 100% accurate, but it is not highly wrong as well. It is good approximation up to 99% as well. You can compute exact value, you will find out that is up to 99% it works fine. So we can take it as a thumb rule that I will just count the degeneracy of fields and I will just multiply with the matrix element mod square, and then other things will just give me small order unity value constants which have to be multiplied, but ballpark central value will be obtained from there. So for any atom, in order to get their transition probability and rate. This Fermi's golden rule is a quick mechanism to get an order of magnitude estimate. I tell you what is the matrix element, you will be able to directly tell me what is the transition rate for this atom. Okay, so let us stop here, and in the next class we will try to see one more feature of quantum field vacuum, which goes by the name of a spontaneous emissions. Okay, so I stop here.